So let's look at an example where we're going to actually find the slope of a polar curve. So we want to find the equation of the line tangent to the curve r equals 2 sine of 3 theta when theta equals pi over 4. So this is a slope problem because to find the tangent line, the equation of the tangent line, we're going to have to figure out what the slope is, right? All right. So to find the slope, which is going to be the first thing we'll have to do to find the tangent line. Actually, it doesn't have to be the first thing, but it's the first thing we'll do. We're going to use these two conversions, x equals r cosine of theta and y equals r sine of theta. And all we have to do to get our parametric equations, I'm not going to put an arrow, I'm going to put an equal sign here because they are equal, is plug the 2 sine of 3 theta in for r here. So x is going to equal what? 2 sine of 3 theta times cosine of theta. And y is going to equal what? 2 sine of 3 theta times the sine of theta. So basically we just take this r function, the polar function, and we multiply it by cosine to get x, and we multiply it by sine to get y. And what we have now, instead of polar functions, we have parametric equations that give x and y coordinates in terms of theta. What values do you think theta will take on for these parametric equations? It's not really given for the polar equation, although we could decide this for the polar equation too. What values do you think it would take on? I agree with 0 to 2 pi. A lot of people will want to say, well, it doesn't necessarily have to go all the way to 2 pi, and this is poor reasoning, so don't start thinking this. Sine of 3 theta actually goes through a full period after 2 pi over 3 radians. But the problem is, this goes through a full period, but theta doesn't go through a full revolution. So we would only have 2/3 of a full circle or 2/3 of a full revolution if we did that. So theta is going to go from 0 to 2 pi, and that's going to give us a picture of the graph rotated all the way around, or going all the way around the origin. All right, so we know what x is, we know what y is. Now we want to find dy dx. So the next thing we're going to have to do is what? Take derivatives. So we're going to do dx d theta. And to find dx d theta, what are we going to have to use here to take the derivative of this? Product rule. So the derivative of the first is what? What's the derivative of 2 sine of 3 theta? Six cosine of 3 theta. So the derivative of the first times the second, which is cosine of theta, plus the first 2 sine of 3 theta times the derivative of the second. What's the derivative of cosine of theta? Negative sine of theta. I know. We could maybe simplify that slightly by factoring out the 2, but otherwise there's not really much simplification we can do there. So let's go ahead and move on to the dy d theta. Again, we're going to have to use the product rule here. So the derivative of 2 sine of 3 theta is what? 6 cosine of 3 theta? Times the second, which would be sine of 3 theta. And then plus the first 2 sine of 3 theta times the derivative of the second, which is cosine of theta. And again, besides factoring out a 2, there's not really any simplification we can do there. So we can move on. the derivative here is going to be a fairly complex fraction, and that's okay. It's going to be something we can evaluate still. So the derivative dy dx is going to be dy d theta over dx d theta, and it's just going to be this this expression on top and this expression on the bottom. The derivatives, a lot of times when we're dealing with polar curves, are going to get a little complicated, but the idea is fairly simple. So it's really important, especially that you keep all your work straight, and that you know the product rule, because you're going to use the product rule almost every time. Since we're multiplying to get x, we multiply by cosine of theta, and to get y, we multiply by sine of theta. So we're going to have the r function times a trig function. You're going to have to use the product rule, but also make sure that you keep things straight. At this point, we want to evaluate it at pi over 4, right? So dy dx when theta equals pi over 4 is going to equal 6 times the cosine of what? 3 pi over 4 times the sine of pi over 4 plus 2 times the sine of 3 pi over 4 times the cosine of pi over 4, right? So that's your numerator. Then in the denominator we're going to have 6 cosine of 3 pi over 4 times cosine of pi over 4 minus 2 sine of 3 pi over 4 times the sine of pi over 4. So if we know those two trig ratios of pi over 4 and 3 pi over 4, it's a fairly simple problem from here on out. So we're dealing with a 45, 45, 90 triangle, right? So we have pi over 4 here. And 3 pi over 4 is a 45, 45, 90 triangle. It's just in the second quadrant. So the 3 pi over 4 triangle is going to be the same triangle but in the second quadrant. So we can use the same triangle and just we'll have to remember which ones are positive and negative in the second quadrant. So the sine of pi over 4, all right, let's just go in order here. The cosine of 3 pi over 4 is going to be what? Yeah, so sine is positive in the second quadrant, but cosine is negative. So the cosine of 3 pi over 4 is going to be whatever the cosine of pi over 4 is, 1 over the square root of 2, but it's going to be negative. So we're going to have 6 times negative 1 over the square root of 2, that's the cosine of 3 pi over 4, times the sine of pi over 4, which is 1 over the square root of 2, plus 2 times, what's the sine of 3 pi over 4? 1 over the square root of 2, and then times, yeah, the cosine of pi over 4, which again is going to be 1 over the square root of 2. And then on the bottom, we're going to have 6 times the cosine of 3 pi over 4. Cosine of 3 pi over 4 was what? Negative 1 over square root of 2 times the cosine of pi over 4. 1 over square root of 2 minus 2 times 1 over square root of 2. Remember, sine is positive in the second quadrant. And the sine of pi over 4? 1 over square root of 2. So it seemed very complicated here. especially with the pi over 4 angle, it turned into a really simple one because cosine and sine are equal for pi over 4. And so now we just have to simplify this to get our slope. First term will be negative 3 because we have 6, and then 1 over square root of 2 times 1 over square root of 2 is going to be 1/2. So it's going to be a negative 3 plus what? Yep, 2 times 1 over square root of 2 times 1 over square root of 2 is going to be 1. And then in the bottom, we're going to have negative 3 minus 1. And so we get negative 2 over negative 4, which is 1/2. Nice, simple answer after all that work. I'm not going to put a box around it because that's not our final answer. We want to find the equation of the tangent line, so we've got the slope of that equation. We still want to find what? We need a point. So how do we find a point? So if we plug in pi over 4 here for theta, then we're going to get our x and our y value for the point that we need. So here we have x when theta equals pi over 4 is going to equal, I'm not going to write this out, but we have the sine of 3 pi over 4, which is what? 1 over square root of 2, times the cosine of pi over 4, which is 1 over square root of 2. So we have 2 times 1/2, which is 1. So that's your x-coordinate. And then for y, when theta equals pi over 4, we're going to get, 2 times 1 over square root of 2 times 1 over square root of 2, which is 1. So we get what point? 1, 1. So the tangent line is going to go through the point 1, 1 and has a slope of 1/2. And you might have to think back a little bit, but the easiest way to write this equation is going to be point slope form. So it's going to be y minus 1 equals slope times x minus 1. And there is your answer. So it turned out to be quite a bit of work because we had to convert it to parametric equations and we had to find the derivative of each of those equations with respect to theta. And in the end, that big, crazy, complex fraction function that we got for dy dx, that would give us the slope of the tangent line at any given point. So we could plug in any value of theta and get the slope of the tangent line. In this case, we get the slope of this green line here, which is going to be tangent to our 3 petaled rows.